Welcome back. We're in Thermodynamics here. This is worksheet 4, problem number 2. I should probably put worksheet 4 up here somewhere. I'm going to walk you through number 2 here and kind of give you an overview of where we're at thus far. I know it's a little bit hard since we're not there together to be able to do any of this stuff together, so hopefully this helps you out a little bit. So let's go through each of these equations here. Q is talking about how much heat, and generally how much heat you've transferred to or from some object. M is just the amount of mass in that object that you're talking about transferring heat to or from, might be like water. C is talking about the specific heat of that object that you're transferring heat to or from. Specific heat is telling us how much energy. If we could see two examples of specific heat over here with both solid water and liquid water. If I took, let's take liquid water here for a second. If I took some liquid water, I pour some out of the tap into a pan, and I start heating that stuff, you know that the water would get hot, clearly. Well, how much energy does it take to increase that temperature? Well, specific heat tells us that. Notice, look at the units here, and I'm going to write out the units here. The units are joule per gram, and then also per degree Celsius. So both of those are in the denominator there. Joule, capital J, stands for joule, after James Joule. And it tells us exactly how much energy. So this is the unit of energy up here. Maybe I should do that in another color there. So this right here is energy. And then we know that grams down here is an amount of mass. So this is, in degrees Celsius is changing the temperature of something. So this is telling us that it would take 4.18 joules, whatever a joule is. It's that much energy to raise that water that's in that pan 1 degree Celsius for each gram of that water that you have. Clearly, if I had a huge pot of water, it's going to take a long time, you'd say, to heat up, versus if I had the same burner and a smaller amount, half of that water, it would take less time for that to heat up. Right, it's dependent on how much mass you have down there, and it's also dependent on how much you're increasing that temperature by. Okay, so that's what specific heat's talking about. And then delta T, I should change back to green there. Delta T is just talking about your change in temperature. So you're all in change in temperature. And whenever you take the change in anything, math class or anything else, you're always doing the final thing minus the initial thing or first thing. That's why in math class, when you went to find the slope of some line there and you said M is delta y over delta x, rise over run, you wrote it like this. You wrote y2 minus y1 over x2 minus x1, and you probably said to yourself, hey, why didn't you do y1 minus y2 and x1 minus x2? And that's because this is the way that you take the change in anything, the difference in any two numbers. You're always taking the ending thing minus the original thing. That's true for your bank account or anything else. Okay, on to the second one. So this guy is just for if I'm changing the temperature of, let's say, liquid water. I'm changing the temperature of just solid ice. Maybe I'm changing the temperature of H2O that's in the gaseous form there, but it's staying within one phase there. Okay, now if we're changing phases, you're looking at this other guy here. H is, that's actually a delta H, that's looking like delta T there at a change in something. Don't worry too much about that. It's technically the change in enthalpy of something. It's kind of a big word there. Don't worry about that either. But it's just saying that, like you've done on the energy plots here, if I have temperature over here and I'm let me get a different color here. If I'm taking, let's say, liquid water and I'm heating, maybe we'll do solid water, I'm heating that up, and then it goes to liquid phase. So this is solid, and we'll do this is the title of this will be H2O. And so then this is a solid going to a liquid, and then this is the liquid, and then it plateaus again, and now here it's the liquid going to the gas, and then here it's the gas. Right, we got all these plateaus here, and let me do the plateaus in a different color here so we can see that. And you go, okay, if I'm let's get this in real perspective here. If I take a pot out of my cabinet and I throw it on the stove, and then I go to the freezer and I grab some ice cubes and I throw it in that pot, solid ice down there, right? If I turn on that burner, right, the solid might heat up a little bit, and that'd actually be pretty hard to see. It probably wouldn't heat up that much. But at some point, it would be going from a solid to a liquid. You would see it melt in that pan. And if you could, it'd be a little bit hard to do in this case, but if you could take a temperature of that solid water that's currently melting as you have that big flame on it, you would find that the temperature doesn't increase. Now, in this case, that's actually pretty hard to do because you'd have to have like a thermometer inside the ice cube, and that's kind of hard to do. But the temperature, but if we actually did that in the lab, which we can do in the lab, oh gosh, then yeah, the temperature actually doesn't increase. And that's true for anything that's going through a phase change, whether it's a solid to a liquid, liquid to a gas, or a gas down to a liquid. If it was running in reverse here and you're cooling something down, whenever you're changing phases, it doesn't change in temperature, even when I'm putting in heat or I'm taking out heat, right? In this case, I'm putting in heat with the flame of that burner, or maybe it's an electric stove, same idea. Or if you're running in reverse and cooling the stuff down, you'd be taking heat out of that substance, but it would still plateau in each of these phase changes. Well, in this case, I'm adding heat to that H2O there, yet it's not increasing in temperature. What gives? Where's that energy in that heat, in that flame going? Well, it's going into the liquid, clearly, and it's causing that ice to melt. It's causing the H2O to go from a solid to a liquid. That energy that you're putting in to the H2O is actually causing it to transform from a solid to a liquid. Okay, so then there's an amount of energy that it takes to go just from one phase to another. Oh, okay, cool. And that's what these guys are talking about. These are the changes in enthalpy of both when I'm taking in heat of melting there. So when I'm taking my solid H2O, and these are all just for H2O, it's different for every compound out there. If I'm taking ice and I'm melting it there, well, I have to add some, look at these units here, I have to add some energy, joules, for all of the mass of that H2O that I have, even when it's not increasing in temperature. Notice it's the same temperature there, and that's why these units here don't have a per degree Celsius there, because it's not changing temperature. It's just an amount of energy to make this, and the heat of melting is really what it is. But sometimes I like to go, oh, that's like a solid to a liquid, or if it runs in reverse, it's going to be the same thing, a solid, a liquid to a solid. It'll be the same amount. It's just whether it's positive or negative, whether it needs to take in that amount of energy or give off that amount of energy. It's the same idea. In this case, in this example, it would have to take in 334 joules for each gram of H2O to go from a solid to a liquid. And if we were running in reverse, so we had liquid water in the freezer and it was cooling down, it would just be, it looked like the exact same thing, but it would be going in reverse here, and it would have to lose 334 joules for each gram of that H2O that was happening there. And now let me change colors a little bit there. And now the same thing is going to be true if I was boiling it. Okay, what does boiling mean? Well, that means I'm going from a liquid to a gas there. Or I could run it in reverse and that'd be going from a gas down to a liquid there. And that's like right over here. So when I look at this thing, that's a liquid going to a gas. Same thing is going on there. If I could somehow take the temperature of that liquid as it's boiling off, and this one's a little bit easier to do. Careful, don't burn yourself. But you could actually try this at home. Take any thermometer, throw it in that water, and you'll notice that it's basically constant. Now, if you actually go and do that, you'll find that the temperature probe will kind of like slightly go up and down, and that's because the pot of water itself is not a uniform 212 degrees or 100 degrees Celsius. The entire time there's like little bits that are a little bit hotter and little bits that are a little bit cooler, even though you're heating and even though the whole thing is boiling. That's why if you actually look at water while it's boiling, you'll notice that when it bubbles, right, when it boils, it's actually like bubbling. And there's like, if you look closely at it, there's like all these points in the liquid that are like the bubbles are coming from. Well, they come from those areas when that specific area is going through that phase change, going from the liquid to the gas. Notice that doesn't happen to the whole thing simultaneously. So that's indicating that those spots that you see the bubbles form from, those ones were at 212 degrees, and all the others were not. They were lower than that. So we can actually see, even without measuring it, that temperature of boiling water is not uniform. It's actually, there's some variation in there. But anyways, if you actually go and do it, you'll notice that there, it increases a ton when it's all liquid. And then once you start to see steam come off and you can see that it's actively boiling here, it basically stays constant over a period of time. And so what's happening there? Well, I have to give a ton of energy. Notice that's like about 10 times the amount of energy to make this thing boil, go to a gas, than it was just to melt it. That's interesting. And so that's what's going on here. So if I need to figure out how much energy is the water needs to absorb to go from a liquid to a gas, well, I'm just looking at, from the liquid to the gas in this case, the heat of boiling there, the change in enthalpy, which is the heat of boiling as they're describing here, is just this amount of energy for every gram of water that I have. Okay, cool. I'm gonna take pause there, and I'm gonna actually get back to worksheet 4, number 2, in the next video.